Welcome to The Explainer. Today, we are digging deep, and I mean that literally, to uncover the secret journey of water and nutrients happening right under our feet. We're going to explore how soil acts as this incredible gateway and filter, a super complex system that decides the fate of every single raindrop. So, here's our game plan. First, we're going to follow a raindrop and see all the places it might end up. Then, we'll get into the nitty-gritty of the physical and chemical gatekeepers in the soil that control everything. After that, we'll look at some smart ways to manage this whole system. And finally, we'll zoom out and see why all this tiny stuff matters on a global scale. All right, so just imagine this. One single raindrop hits an open field. Seems pretty simple, right? But what happens next is anything but. Let's trace the four main paths it can take, which really form the foundation of the whole soil-water cycle.
In this diagram, it just illustrates that principle perfectly. You've got this water balance in action. Every drop that comes in as rain or snow has to go somewhere. And the soil, well, the soil is the great decider. It's what splits that water into all these different paths. It's a constant balancing act.
So, as you can see, every drop of water has one of four possible destinies. It can run off the surface, which happens a lot on hard, compacted ground. It can infiltrate, soaking into the soil to become moisture for plants. It can percolate, draining way down deep below the roots to recharge groundwater. Or it can go right back up into the air through evaporation and from plants breathing, a two-for-one deal we call evapotranspiration. Okay, let's zoom in a bit. The actual physical structure of the soil, it creates this incredible, complex labyrinth that controls how fast water can get in and move through. These are the physical gatekeepers that direct all the traffic. You know, soil texture is really the first and maybe the most important gatekeeper. And a great way to think about it is this. Sandy soil, with its big particles and large open spaces, we call those macropores, it acts just like a colander. Water zips right through. But clay soil, with its teeny tiny particles and small spaces, the micropores, it acts more like a sponge, holding onto water really tightly and letting it through very, very slowly. And this graph shows that trade-off perfectly. See these curves? They show how hard you have to pull to get water out of the soil. Notice how that clay soil line stays way up high? It's holding a ton of water, but it's holding on for dear life, like a stubborn sponge. The sandy soil, on the other hand, just lets its water go with almost no effort. And that is absolutely crucial for understanding how much water is actually available for a plant to drink. Now, it's not just about texture. We also have to talk about compaction. When you get heavy equipment or too much tillage pressing down on the soil, it's basically a massive traffic jam on a superhighway. It literally crushes those big macropores we just talked about, the express lanes for water. And when those lanes are closed, well, the water has nowhere to go. It just backs up on the surface, causing puddles, runoff, and erosion. Okay, let's switch gears from the physical world to the chemical one. If water is the vehicle driving through the soil, then nutrients are its passengers. And soil chemistry does this kind of chemical handshake that decides which nutrients get to hitch a ride and which ones get left behind. The key idea here is something called cation exchange capacity, or CEC. The easiest way to think about it is as the soil's nutrient Velcro. Tiny little particles of clay and organic matter naturally have a negative electrical charge. This lets them grab and hold on to nutrients that have a positive charge, keeping them right there in the root zone where plants can get them. So these positively charged ions, or cations, are what we call the sticky nutrients. It's simple physics. Opposites attract. They cling to those negatively charged soil particles. And this is so important because it creates a nutrient reserve that doesn't just get washed away or leached the next time it rains. But on the flip side, you have the anions, the slippery nutrients. Now, these also have a negative charge, so they get repelled by the soil particles, kind of like two magnets pushing each other away. They just don't stick. They stay dissolved in the water, which makes them super mobile and really easy to lose from the root zone. And that means they could end up in our groundwater. And this is where it all comes together. Organic matter is an absolute powerhouse for holding on to nutrients because it dramatically boosts that CEC, that nutrient Velcro we talked about. At the same time, you've got soil pH playing a huge role. A nutrient like phosphorus, for instance, is only really available for plants to use when the soil pH is in that sweet spot, right around neutral. Okay, so we've got the physics and the chemistry down. So what do we do with all this information? How can we manage our farmlands better? How do we work with the system to keep that precious water and those valuable nutrients right where our crops can use them? This table lays it out beautifully. The big goal is to build up soil organic matter. Sure, you can add stuff like compost and manure, and that definitely increases the gains. But what's even better are practices like planting cover crops and reducing tillage. Why? Because they're a double whammy. They add organic matter while also cutting down on the losses from erosion. It really all boils down to these four interconnected ideas, which you might hear called the principles of soil health. 1. Keep the soil covered to protect it from the weather. 2. Disturb it as little as possible to protect its structure. 3. Diversify your crops to build a stronger system. And 4. Continuously feed the life in the soil with organic matter. Now check this out. This is a really clever bit of engineering called in-field rainwater harvesting. By creating these little basins and using mulch, the system actually captures and concentrates any runoff. It forces that water to soak deep into the soil, storing it safely away from the sun, where it won't evaporate. It's a brilliant way to make every single drop of water count, especially in drier climates. All right, let's pull back and look at the big picture. Why is it so unbelievably important to understand and manage these tiny microscopic processes? Because their impact is anything but microscopic. This quote really cuts right to the heart of it. When we don't manage our soils well, the fallout extends way beyond the farm. Those slippery nutrients like nitrate that we talked about, they contribute to what's called non-point source pollution. Basically, pollution that doesn't come from one single pipe, but from a huge area like a field. And that can do real harm to our rivers, our lakes, and even our drinking water. And this gets us to the most important takeaway. Healthy soil is not just dirt. It's a living, breathing ecosystem. It's a dynamic sponge. So when we manage for soil health, we're not just trying to get better crop yields. We're actually building natural infrastructure that cleans our water, recycles nutrients, and supports a more resilient environment for every single one of us. And that leaves us with this final, critical question. Understanding this hidden journey of water and nutrients gives us the power to be better stewards of the land. By seeing the soil for what it truly is, our most valuable living filter, we can start to manage our lands not just for short-term gains, but for long-term health and resilience for generations to come.